So if you want to implement such kind of circuit where whenever I am going to give some input from here, you will have output, right? When this is high, you can transfer whatever input is available to the output, right? Then you can use such kind of structure without having any problem. Here you can give some clock signal which is running from minus V supply to plus V supply. For minus V supply, this is off, so this is open in cutoff. When it's on, you are another side, right? So this is how you can use it. But if you are interested in amplification, so I want this. So are you getting? Are you interested to learn this, or like this is not part of course, but I am telling you. Okay. So what exactly I want? I want to amplify my signal. This is what I want. If I want amplification, what region of operation should I choose? Komal, what do you think? Active, right? So active mode of operation I need to choose, means I am going to my transistor in active mode, or I am going to choose the Q point or the operating point exactly when it's in the regime of active mode. Here, or maybe here, wherever you like, you can keep it. But if you are this side, it's just a switch, there is no amplification. Okay, so if I want that, this is the signal which is going to get amplified, and this signal is generally small by nature. Small means there are two kinds of signal: small signal and large signal. Do you remember this? Yeah. So what do you think, Nikita? Do you remember small and large? So okay. So if there is an amplifier whose gain is multiplied by 10, if input is 1 millivolt and this side supply volt is 1 volt and this side is 0, so output is 10 millivolt. But if I am giving input of, let's assume that 0.5 volt, output is not 5 volt but it's 1 volt, so it gets saturated and this is large signal. So I am talking about that small signal which I am going to feed here. That small signal will make sure that the output will not go beyond VCC or minus VE, right? So this signal is small, might be in millivolts, right? So can this small signal guarantee to make this transistor in on mode or in active mode? The small signal at least 0.7 volt, at least 0.7 volt, right? So this signal might be very small, which cannot solve your purpose. So what I am doing, just to solve that purpose, I am adding two resistances. Let's call them R1 and R2. This side some value of VCC will be there. By tuning the value of R1 and R2, you can have some DC voltage on top of which this small signal is riding now, right? But there is one small problem. Can you see a small problem? No, there is no capacitor right now. So my question is, are you going to see here as, so here what you should see, VCC times R2 divided by R1 plus R2. Do you agree with this? Right? But are you going to see exactly that much voltage or something else? I am saying that there are R1 and R2 two resistance which are going to make sure that this point will be in active mode by any in this region by tuning the value of R1 and R2. That is going to be done by this VCC and R1 R2. So here you are going to see some Vx potential which is equal to VCC times R2 by R1 plus R2, right? You are following till now? But I am saying that you are not going to see this one. Why? Okay, this is the question. Where is resistance? V and VCC. Where is V? Vx and okay, this one Vx and VCC. There is a resistance. Yes. Another side. It's not going to disturb you, right? Hmm? Small signal. Okay. So, what is that small signal? You mean to? So you might be correct, but can you elaborate what you are saying? Hmm. Okay, so there is a current. Same current is. Okay. Where? Okay, so you are saying it's small signal, maybe going this side, but it's very small. Look, this is an assumption that IC is equal to IB plus IE, where IB is equal to 0. Now you are happy. Still, I am saying that you are not going to see this one. You are going to see something else. Your question like reasoning was correct, but IB is 0 or very small. Your direction of thinking is correct. At that point, the small signal with that VP, that voltage plus this voltage. Yeah, so it has to be Vx plus Vin, but we are applying superposition. Look, when we are doing DC analysis, so DC is available. When we are doing AC analysis, AC is available. We are going to add both of them, right? So it will be Vx plus V for sure, because we want to amplify this V. Vx will be different than what has been written here. But how? Divanshu got correct reasoning that this current has to be shared by some other current. So I am saying like this current and this current, if both are same, then this is going to happen. But if there is IB current, yeah, you will lose something. But I am saying IB is equal to 0. Then current might go in this direction. So what you are seeing in this direction. So I want to tell you one thing. Whenever there is something called input, always consider that input is not coming by magic. It's coming by something called function generator. So function generator is going to give you whatever you want at the input. But as Divanshu told, there might be current going in this direction. If this side is high impedance, no problem. But there is some impedance, and what was that impedance value? 50 ohm. So you are going to see something like this. Are you agree with me? Right? So this will be 50. By the way, I am telling you one more thing. You must have seen it in your textbook of school textbook. R1 and R2 has to be very high value in mega ohms or maybe hundreds of kilo ohms, just to make sure that IB is 0, because this is going to happen just to make sure IB is equal to 0. So this is very big value compared to 50 ohm. 50 is winning, so R2 in parallel of 50 is going to be 50 approximately. So that is what I am writing here. So 50 plus R1. So you are not going to see exactly what you wanted to see, but you will see something much lower value than what you were expecting. So what is the suggestion? How to modify this circuit to make sure that you are going to see Vx equal to VCC times R2 by R1 plus R2. Now you can say Piyush. Huh? Yeah. So use a big capacitor here. This will block the DC current which is coming from here. But when you are applying AC analysis, this AC will go that side. So it will allow only AC from input side and will block DC from top side. Right? This is how it works generally. Right? So now there are two things. One is called small signal plus DC value, which is available here. I'm only interested in these two things. If DC is higher than 0.7 volt, I'm happy. I'm in active mode. And I want to amplify small signal. Small signal is very small. It might be in millivolt or maybe 5 millivolt, 10 millivolt. That will be the range in reality. And that is what you want to see as an amplified version. If you want to do this and we are interested in only small signal, instead of calling it just Vin as an input, but we are going to call it something small, something like this. Small value of input which is going to be changed, whose derivative is not zero. This is what we are interested in. So all the analysis where you want to apply Z parameter, Y parameter or any parameter, you are not supposed to write down the equation which is like this, where y11 is equal to plain V1 by I1, but in transistor it is going to be renamed as del I1 by del V1. Similarly, y12 is del I1 by del V2 and y21 is equal to del I2 by del V1 and y22 is equal to del I2 by del V2. By the way, this analysis is not given in any book. Okay, so please follow what I am writing here. Okay. Because it's small signal. If I am taking normal one, it's very small value which will be counted as DC. These values are DC. I am doing the small value which is AC. Just to distinguish AC and DC, we are going to make sure that derivative is not getting zero. So derivative is going to represent the small signal. Okay. So now, as I told you, in new era, all circuit designers are using Y parameter rather than H parameter. H parameter is the next study of our network theory. But before going to that, if you are going to use Y parameter, where you are going to have following equation y1 is equal to del I1 by del V1 and so on, I can apply same thing to a BJT. Where do you remember the BJT equations? Some of the equations. First of all, we can draw how does it look like. This side is base, emitter, collector. Right? I want to replace the whole thing using two port. So that is going to have following things. One is IB, one is IC, this is VBE and this is VCE. So it's similar to what we were doing in two-port network. So in this black box, there is 3-terminal device, but it will be converted to two-port network using our analysis. And you are going to have following things. You are going to have one resistance and something in parallel which is current. This is current, this is resistance, this will be emitter, this will be collector, this will be base, and this will be VBE, and the current which is going in is IB. At the output side there is current IC, and this potential is VC, and this value is going to be, so it's y11 times V1, so it has to be 1 by y11, and this has to be y12 times V2, so this will be y12 times VCE. This side it will be 1 by y22, and this will be y21 times VBE. I replace all this V1, V2 with VBE and VCE, all I1, I2 with IB and IC, right? But I need to know the equations. Do we know the equations for this transistor? Current equations means IB and IC are known to us or not? Is it known to us or not? Do you remember what was the, okay, just for your information I'll write it down. Whatever the IB will be there, IC is nothing but beta times IB. Beta is current gain, IB is, now can you write down IB? You must have studied in, at least in diode equation. So look, if you look at here, when this transistor is in active mode, when this transistor is active mode, this is forward bias, this is reverse bias. Here to here junction is reverse bias, here to here junction is forward bias. It will follow the diode equation. What you are saying? So VBE by VTH. Minus, okay. That is one equation I found from one book. So is it wrong or correct? Yeah. So I haven't ignored. I copied from some device book and I kept it here. So now following these equations, which are exactly the one which we have studied, where V1 is equal to VBE, V2 is equal to VCE, I1 equal to IB, I2 is equal to IC. If that is the case, and we have one equation is already available to us, IB is equal to I0, instead of calling I saturation, I call it I0 times exponential of VB by VT minus 1. So can you find out these four parameters now? In the equation of IB, there is no VC. Can you see anywhere VC? VC is not available, right? VC is not available. In both the equation, VC is not there. So if you are taking the derivative with respect to VC, that will go to 0. Anything with respect to VC, it will be 0. You need to find out only two parameters. So what is y11? Del IB with respect to del VB. So are you getting this? If you are getting this, I can rewrite it in terms of IC is equal to IC divided by beta times VT. Right? Similarly, you can write down y21 is IC by VT because beta will be gone. I am going to rename these two as one. I am going to call R pi. Okay, actually, it has to be 1 by R pi. I am calling this pi because this is part of pi network. That's why let's call it R pi. This is going to be transconductance, which is going to be defined by IC by VT, where VT is threshold voltage. Okay. If I replace all of them in two-port network, I am going to see this one. If you remember, like at the initial time we used to draw this one, right? So your transistor is like this. Wherever you are saying transistor, you have to replace this with this structure. But this is possible when it's Y parameter. You can replace same thing using Y parameter but T network. That is also possible. Similarly, you can replace with the Z parameter, and similarly you can replace with ABCD parameter or some other parameter. But we like Y parameter because directly the impedances are possible to see. Okay, so now can you tell me what is the impedance if I'm looking into this system, which is exactly equal to Z11? Do you agree with me? Because Z11 is V1 divided by I1, right? If this is V1 and I1, rest of the things are 0, right? So that is going to give me Z11. Similarly, if I'm looking from here, Z22 is going to give me output impedance, right? So if I know these impedances, Z out is equal to what value, by the way, you are going to see at the output side? When you are looking at the output impedance, what are you going to see? Let's apply Thevenin wherever you want to see the impedance, or if you don't follow that, you can apply Z11, Z12, whatever theory you like. Gaurav, what are you going to see here? Okay, let's look at here, which is much more easier. So, what are you going to see here? R pi, very good. Z in is R pi. What are you going to see at the output side? Infinity, very good. Right? Output is infinity, input is some finite value of R pi. So, this kind of structure is, I made mistake here. It has to be correct. I made mistake. Because input is low, output is infinite, right? So it's a current control, current source, right? Okay, but in reality, this is not going to happen. You are going to have some load resistance. Do you agree with me? There will be some load resistance. So this output impedance will be, Aishwarya, what will be the output impedance now? RL, right? So let's write down these two things here. Now I know that output voltage is nothing but output times output current, and input voltage is input times input current. So if I'm interested in the gain, which is low frequency gain, I can write down this as you might have seen this formula somewhere, right? So there are many ways to derive it. This is one of the way. So depending on Rn and Rpi, all this can be done. But still, this is with some of the approximation where we have not considered some of the things like base width modulation. I don't know whether you study base width modulation. Then there are some approximations which we have not considered here. So all the first order effects have been taken. Second order effects have not been considered. So this is just a plain simple model where it is only applicable at low frequency. This is only applicable at low frequency. Do you agree with me? It will be low frequency model only. This is only at low frequency. Tell me, Gaurav. Okay, let's revisit what we have learned earlier. If there is a capacitor in your system, means there are two dissimilar plates, and on top of everything, you are working at high frequency because capacitor at low frequency is actually open circuit. So right now, I can see three dissimilar plates. Can you see three dissimilar plates? Base, collector, and emitter. All are dissimilar. If you are working at high frequency, you should see three capacitor. I am making it dotted because they are not visible, but they are there, and we are going to call them as parasitic capacitor. And this will be CBE. This will be CBC, CBE, and CCE. But people don't like this CBC. They like to call this one as C pi because it's connected between pi. This is high frequency model. Earlier was low frequency model. So if you're interested so much in high frequency or you want to find out the bandwidth, then you need to go through high frequency model. So do you have any question just in the derivation of this two-port network of BJT? Right. So you can replace this and you can do all the analysis which you want in any circuit. Just for very quick review, if I want to derive the Y parameter for MOSFET, there are two equations. Ig is equal to 0, and so there are three terminals. This is called gate, this is called drain, and this is called source. Gate current is 0 and ID is equal to IS, and ID is equal to mu n C ox W by L VGS minus VTH square, where all these terms are constant. This VTH is threshold voltage, this is also constant. Let's replace this with one name. Let's call this one as Kn. Then you can find out, and you can, when you are going to do this, you are not going to observe Y11 and Y12 because gate is already 0. So there is no point in writing the gate equation in terms of VGS and VDS. Everything is 0, is equal to 0 VGS plus 0 VDS. Right? So there is no need to take derivative. For this one, which is Y21 times VGS plus Y22 times VDS, in this equation, I am not going to see VDS, so there is no point in looking at VDS. So there is no Y22, there is only Y21 which has to be found out. When you are going to find out Y21, when you are going to find out Y21, Y21 is nothing but del ID by del VGS, right? So Kn times right. This is what you are going to see, and you are going to call this one as transconductance. This is the transconductance of this particular transistor, and you can replace this with following structure. Oh, I'm confused. Just for like completeness, if you want to know why gate current is 0, it's depending on one fact that, do you know band bending diagram? You heard about this? Valence band, conduction band. In your school, you must have some bands are available. Energy bands, energy band diagram. Okay, so at higher level people call it band bending diagram because band is like energy band is getting band diagram. Right? So for any transistor or any network to work, it has to make sure that from valence band to conduction band there is sufficient energy for electron to move. If there is no energy or there is wide band between these two energy bands, then it cannot go, and that is happening in MOSFET, and you are having zero gate current because it does not have sufficient energy to take electrons from valence band to conduction band. Right? Regarding this, like there is one course called 301, ee301. If you are so much keen in learning this, it's called device electronics for integrated circuit. It's all talks about just device physics. Okay, so you can study this if you are interested in that particular field and to understand why Ig equal to 0, where you need to understand Schrodinger equation and all this charge sheet model. Through that you can derive it. It's only about this. Why are you laughing? Huh? Okay. This is just for your information and the completeness. So the device electronics for integrated circuit. So right now this is being taught by Kunal Ghosh. Okay. So he is going to uh, Himanshu. Device electronics course code is 301 or something else. 301, yeah. Oh, 301 is control. Okay, then 3xx. But are you following rest of the things? These some of the things which I talked about device physics. That was just for your information, just for the completeness. This got recorded, so you can hear it anytime, right? And you can re-hear it again and again and try to understand. If you are getting any difficulty, you can contact me again.